Hello everyone. Today we have a discussion of PN junction solar cell. Finally we came to this point when we can discuss photovoltaic operation mode of a PN junction, and that's actually solar cell. Photovoltaic means that we generate electricity when we shine light on a PN junction in particular. That could be different device configuration. However, PN junction is the most classical and originally used semiconductor device in photovoltaic mode. So first publications appeared in something like early 50s with quite low efficiency, like few percents, but they already clearly have shown that it's possible to convert light into electricity, and since then it was only increasing the performance of solar cells, which is continuing up to now. So everything started from PN junction. Now we have many different device configurations, different materials that started everything with silicon PN junction. So that's why we also want to get the understanding of solar cell on example of PN junction technology. So before we go to PN junction, I would like to start with such positive slide, sunny, and the question is to understand what's actually sunlight, which we experience every day, and what kind of properties it possesses. So we need to quantify it somehow. It's not bright and dark, definitely brings more information in it, and that is definitely relevant for solar cell application. So if you look at this dashed line, like black dashed line, that is the spectral distribution of absolutely black body at temperature 5250 degrees Celsius. So that is more or less, is all of course not uniform and not constant, but that's some average temperature on the surface of the sun. So matches quite well with real spectrum, because real spectrum in space, which is shown as AM0, so it's this curve here, matches quite well, but of course there is some difference because of absorption of light in the material of the sun itself. Also, these non-uniform temperatures. There are regions with lower temperatures, regions with higher temperatures. So there is some discrepancy. So what we have here on this axis Y is spectral irradiance. So we have watt per meter square per nanometer. So we have it from like something 100 nanometers up to 3,000 nanometers. So that is quite broad spectral range. That's all electromagnetic waves in this spectral range, which are bringing some energy from sun to the surface of Earth. If we are talking about surface, then we should address M1, and that is condition when we take into account absorption in our atmosphere. So there is some atmosphere in, luckily, in between space and us on the surface of Earth, and because of the gases which form atmosphere. By the way, what is content of atmosphere? Any suggestions? Like in terms of like composition, in gas composition. Nitrogen, and what else? Oxygen. Most of these two. Now we are working hard to increase CO2, but hopefully it will not become comparable in concentrations as oxygen. But what is the ratio, like what percent? Nitrogen and... Okay. Okay, and then 20 something oxygen. So we also have a lot of water, like H2O, in atmosphere, which results in this like absorptions here in IR region. So that's why we definitely get less of sun light power on the surface of the planet as we do in the outer space next to the planet Earth. That is a result of reflection light from atmosphere and absorption light in our atmosphere. And here we don't have spectrum for AM1. So AM stands for atmospheric mass. It just tells us how what is the length of the path of sunlight through our atmosphere. So AM0 means it doesn't go through atmosphere at all. AM1 means the light that sun is located just over our heads in the zenith. So that's kind of conditions for equator, when there is no shade casted by object, just sun is over us. And there is also commonly used for calculating performance of solar cells AM1.5. So as you see, it stands for some angle 48.2, which is like middle altitude angle for like actually quite close also to our location in terms of this altitude, and means at this angle the path which sunlight goes through the atmosphere is larger than with angle 0 for AM1. So obviously it will absorb more, and we will get a bit less intensity. So that is this black solid line, like this one, is actually AM1.5 solar spectrum, which reaches on average the surface of our planet, and this energy brought to us from sun can be converted into electricity. It's another question how much of this spectrum we can convert, how much we cannot. We will discuss about this later. But this is total. If we integrate this, so we can integrate all over the wavelengths, we can consider from 0 to, let's say, 3000, or even infinity, doesn't matter, because you see it just vanishes here at long wavelengths. So when we integrate this, we will get total intensity of sunlight, and that will be for AM1.5 is considered to be 1000 watt per meter square. You see, we have watts per meter square. We don't have these nanometers in the denominator, because when we integrate, we kind of multiply by these nanometers, we get rid of them. So so that is the difference between total light intensity and spectral irradiance distribution. It's per nanometer. So you can pick up any wavelengths and check in this narrow wavelength region, plus minus delta lambda, how much light at this given wavelength is coming to the surface of the Earth. You just have very narrow integration range. But we want to know, in order to calculate performance of solar cells, we need to know total energy which comes to us, and then with respect to this total energy, like the intensity energy per per square meter per second, we will calculate later performance. So that is what you need to know about sunlight, because we obviously work with these parameters when we operate with solar cells. So now let us consider our old good friend p-n junction under equilibrium conditions. And we remember that we had a lot of majority charge carriers in holes in p-type region and electrons in n-type region, and very low concentrations of minority charge carriers, electrons and holes in p and n-type region. So at thermal equilibrium we have flat Fermi energy all over the p-n junction, and this diffusion of majority charge carriers currents, they are compensated by drift currents of minority charge carriers. So they are both small. So why they are small? Maybe you can tell me why they are small.
Which one?
Like,
minority.
So we have equilibrium. We have diffusion currents of majority charge carriers are equal to drift current of minority charge carriers. But under like dark, both of these currents are small. So can you explain me the reason why they are small?
Dark, the minority charge carriers.
What is with them?
Because like under dark we have less charges that are generated from these sides. You know,
Yeah.
small minority carriers removed.
So we have low concentration of minority charge carriers. With that, we just cannot physically create a large current. So, okay, that's a valid statement. What about majority charge carriers? We have plenty of them.
Yeah, because
So, but that kind of doesn't fit to your logic. If we have little, like small concentration of minority charge carriers, we have small current, drift current. That makes sense. But at the same time, we have plenty of majority charge carriers, and we still have small current. So what's going on there?
because maybe they are not really diffusing, because if current comes by either drift or
Okay. So minority drift and majority diffuse. And why, if we have a lot of majority charge carriers in neutral regions, why they don't diffuse intensively and create large diffusion current under equilibrium condition?
they don't have, because they don't have much.
There is a driving force. Here we have a lot, and here we have little amount. So there is driving force, there is gradient of concentration, but under equilibrium something happens, and they don't diffuse much. They reduce the diffusion rate, so that this diffusion current becomes equal to small drift current, and they in the opposite directions going and compensate each other. So what's the reason why diffusion current of majority charge carriers does not contribute much and remains small? So we were talking about the formation of p-n junction. So initially that is the case when we just put together two pieces of semiconductors. They start to diffuse, and this current, diffusion current, is huge. But something happens. We build up space charges in n and p-type semiconductor. These space charges are formed by immobilized ionized donors and acceptors. These space charges create internal electric field. Internal electric field, which is linearly, we have shown that it's linearly distributed, creates quadratically distributed potential difference, electrostatic potential distribution within the depletion region, and that results in the potential barrier for the diffusion of majority charge carriers. So the reason why we have from one side high concentration of majority charge carriers and from other side still small diffusion current is that we have this potential barrier. This charge carrier should go over this potential barrier in order to go from neutral N region to neutral P region. They want to go because of concentration difference, concentration gradient, but this potential barrier, which is Q times VBI, doesn't let them do this. So these guys you should know. So now, that's what we have in the dark, thermal equilibrium condition. Now we bring some light, and what happens? We don't change much concentration of majority charge carriers. They remain more or less the same. They already work very high. But we increase dramatically concentration of minority charge carriers. So, coming back to our previous discussion, we claimed that drift current is small because of low concentration of minority charge carriers. But what happens now? Drift current will significantly increase because concentration of minority holes and electrons in N and P regions significantly increased because of photogeneration. So these are minority non-equilibrium charge carriers already. So their concentration is much higher, and this drift current increases a lot. So now let us think what will happen if we keep such p-n junction under open circuit condition. What means drift of minority, let's say electron from N type region to like through the p-n junction? It means that this, minority, not electron, but minority hole from N-type region drifts through the p-n junction to the P-type region. That means that a hole from here, that's minority charge carrier, it moves to P-type region because of drift, because of internal electric field. Here we have this field, electric field. And here we get some excessive majority charge carrier. It was minority in the N-type region, but now it's majority in the P-type region. We have plenty of these guys. They all drift, they move here, and they don't recombine here. It's not minority charge carrier, which I told when it diffuses, majority goes to another side, it becomes minority, and then it recombines very quickly because it's compensated immediately. Its electric charge is compensated within the extremely short interval of time, which is Maxwell relaxation time. Its like existence as a charge, even compensated charge, ends within the recombination lifetime. It meets with majority charge carrier and recombines. But these now, they are majority charge carriers, they don't recombine. And they kind of accumulate in this region. So similar happens here when we have electron as minority charge carrier in P-type. It drifts to N region, and here it becomes majority charge carrier. Also does not recombine because it's majority charge carrier, so it starts to accumulate. So eventually, because of such drift currents, what happens under illumination? What we have? We have some excessive positive charge in p-type region because we have more majority charge carriers, more holes here than negatively charged acceptors. So we, in total, some net charge is positive in this edge of the p-n junction. In previously neutral region, now it's not anymore neutral because we have more holes than negatively charged acceptors. And the same, we have some excessive, like net negative charge in the n-type region. So what is this? Any suggestions with what such a picture? Do you have some association with what we considered before when we have excessive negative charge and positive charge at the edges of p-n junction? Capacitors, yeah, so it's related to, so you kind of jump over few steps. So capacitor changes because of changing of the depletion region, and depletion region changes because of applying external bias. We apply external bias, and applying external bias is actually applying some negative potential. Let's say what we had before. Here we have excessive negative charge, here is positive. So it could be modeled as we don't shine light, so we have some shutter here, so it remains in the dark, but we apply negative potential to n-type region and positive potential to p-type region, external bias. So from here we see that there is a correlation between p-n junction in dark under forward bias and p-n junction under illumination without any bias. It just creates this bias because of excessive negative charges at the edge of the n-type region and excessive positive charges at the edge of p-type region. So because of diffusion of significantly increased concentration of minority charge carriers through this p-n junction, we start to accumulate in open circuit condition. You see, we don't hook up here any resistor, load resistor, under open circuit condition. We start to accumulate this diffused, this drifted charge carriers as majority charge carriers already in the opposite sides of the p-n junction, and they create some like space charges, which act as we would apply external bias. So what happens here? Here is depletion region, and here we have this internal electric field. Internal. So it goes from right to left, because it goes from positive charge to negative. And now we have excessive positive charge at the edge of p-type and negative at the edge of n-type. So that's why we create external electric field, which goes in opposite direction to internal. So that is forward bias. So that's why you need to understand that every solar cell which is under illumination, so its p-n junction, is under forward bias. So that is how it works, and that's the quite detailed explanation why it happens. So you need to understand this mechanism. So I told you earlier that if we shine on p-n junction, when we discussed this surface recombination, that the solar cell or Schottky junction is under forward bias, but didn't give explanation. So this is a detailed explanation why every p-n junction under illumination is under forward bias. So now let us consider also under open circuit conditions charge carrier concentration profile. This is also a very important figure, which I would recommend you to understand and remember. So with these solid lines, like red and blue solid lines, we have distribution of charge carriers profile in the dark. So we have high concentration of majority holes in neutral p-type region. Then it goes from depletion region and it drops to low concentration of minority holes in n-type region. The same, like not the same but opposite but similar, majority electrons, high concentration in n-type region, goes through depletion region and end up with low concentration of minority electrons in p-type region. So that's under equilibrium condition, and now we have some sunlight hitting this p-n junction, and what happens? We don't change much majority charge carrier concentration. These guys remain pretty much constant because their concentration is already very high, but we significantly increase minority charge carrier concentration. So it goes from equilibrium NP0 to non-equilibrium NP, and PN0 to non-equilibrium PN. Their concentration under open circuit condition can be defined as the product of recombination lifetime of minority charge carriers, in this case it's tau p, recombination lifetime of electrons in n-type region, times G. This capital G, that is generation rate. That tells us how many charge carriers, electron hole pairs, are generated per unit volume, per unit time. So another, we can also, from other side, we can define concentration of these non-equilibrium minority charge carriers. They are still minorities, they are much lower than majority charge carrier concentration, but much higher than equilibrium minority charge carrier. So it's a product of tau n times G. So where it comes from, we can write that dn over dt under open circuit condition should be defined by generation rate minus recombination rate, because we don't have any current. J is equal to 0 under open circuit conditions. We don't have current. Current is equal to 0. So from here we can write that J is equal to R. So we recombine everything what we generate, and this recombination can be expressed as concentration of charge carriers under open circuit condition. Let's write open circuit condition divided by recombination lifetime tau. Let's say this is for electrons and we put tau n. So that's why this steady state concentration of photo-generated charge carriers under open circuit condition, NOC, should be equal to tau n times G. So that's how we can determine concentration of these minority charge carriers. However, we need to focus our attention on the profile of this minority non-equilibrium charge carrier concentration. So here, far in the neutral region, you see that we have flat. So it's kind of flat here, doesn't change. It's just equal to this tau n times G. The same stands for flat concentration profile tau p times G in the n-type semiconductor. However, when we come closer to the p-n junction, within this distance Ln, diffusion length of electrons from p-type side, to and also Lp, which is diffusion length for holes from p-type, we see that this saturated level starts to drop. So we go down here and here. Any suggestions why this happens within the distance which correlates like from edges of p-n junction, of depletion regions of p-n junction, at the distance scale of diffusion length of minority electrons and holes? why it goes from higher concentration, which is flat, far away from p-n junction, why it decreases when it approaches edge of p-n junction.
Because they are recombined back, the depletion and the depletion layer.
Oh, I mean, they recombine everywhere. They recombine here even more in far region of neutral part of this device, because this guy, tau p and tau n, actually tells us how fast they recombine, because it tells us how long they can live there. So they recombine quite efficiently everywhere because they are minority charge carriers. But because of some reason, their concentration reduces as we approach close to the p-n junction. There is something different from recombination. We mentioned about...
There was like another scenario.
So that was when we apply forward and reverse bias. For equilibrium, we go from equilibrium to non-equilibrium conditions when we increase or decrease concentration next to the p-n junction. So here we decrease their concentration of this non-equilibrium photo-generated minority charge carriers because of drift. Don't forget, here inside of the depletion region we have strong electric field, and this electric field kind of extracts charge carriers, so it extracts holes from n-type region and extracts electrons from p-type region. So it creates this drift current, and the more it extracts, the more it will be reducing its concentration next to the p-n junction edge. And that's why we will create some gradient of concentration of minority non-equilibrium photo-generated charge carriers next to the edges of p-n junction. So that gradient is because of this reduction of concentration as we approach from far neutral region closer to the edge of the p-n junction. And that happens in the scale of diffusion length. It's actually during this diffusion length is distance during which charge carriers can move. As we define definition of diffusion length is distance minority charge carriers can move in semiconductor before they recombine. So obviously further, if we go further from the edge of p-n junction to the neutral region, they cannot come from here to here. Because distance is too big, they will recombine on the way. So this electric field, which extracts charge carriers, will not have impact on charge carrier concentration profile deeper in neutral region than this diffusion length LP. And the same for electrons, but Ln.
So this diffusion length kind of dead zone, yeah?
It's the region, defines the region next to p-n junction. Next to edges of of the depletion region of the p-n junction, in which we observe diffusion of minority non-equilibrium charge carriers. Because here we have it flat, there is zero gradient. But here in this region, which is defined by the thickness of the by the diffusion length of minority charge carriers, we see gradient of concentration because of extraction of these minority charge carriers by internal electric field in the depletion region. We create this gradient of concentration, and as a result we have diffusion of minority non-equilibrium photo-generated charge carriers, which contribute to photocurrent, because that's what we collect all of them, and they all contribute to photocurrent of solar cell when we actually go for some resistance attached to this solar cell. So that's why we have three components of photocurrent of a solar cell. We have drift current of minority non-equilibrium photogenerated holes in N-type region. Then we have diffusion current of minority non-equilibrium photogenerated electrons in P-type region. And also we have drift current, because if we also generate charge carriers here in the depletion region. So it also absorbs light and we can generate electron holes. If we create here this electron hole pair, then this internal electric field will very efficiently separate them and contribute to the photocurrent as a drift current through the within the depletion region. So we have three contributions. Neutral regions at the thickness, within the thickness of diffusion length, contributes via diffusion currents, both N and P type, because of diffusion of minority non-equilibrium photogenerated charge carriers. And also depletion region contributes to this photocurrent via drift current of photogenerated charge carriers within the depletion region. So that is the origin of three components of photocurrent. Now let us try to figure out how we can quantify them. So here you can see, that's actually from the physics of semiconductor devices, some like general structure of a solar cell. What do we have? We have p-n junction, so we have p region and n region, so it's considered on silicon, like classical technology. On the surface we have some anti-reflecting coating. So why do we need anti-reflecting coating?
So that we can absorb more.
Obviously, we don't want to have reflection. We want all light to penetrate in our p-n junction and generate charge carriers. Also, we need to collect these photogenerated charge carriers, this photocurrent. We need to collect and in external electric circuit, because eventually we want to hook up some load resistor here. So our load. And from one side we want to have very good collection of these charge carriers, but from other side we don't want to cover the solar cell surface, because this region where we have metal grid, it's shaded region. So here underneath, like here, 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 we don't have any light. So we want to find some compromise between shading of our solar cell and having these metal rods close enough that photogenerated charge carriers can reach them before they recombine, so they are collected by this metal grid and contribute to some current in external circuit. So that is general device configuration of a solar cell. And here you can see the equivalent circuit of an ideal solar cell. So what is this? It's our p-n junction in form of diode, on which we have some light shining with h nu energy larger than Eg, band gap of the semiconductor this p-n junction is made, and our load resistor. So usually we don't show this in such manner. We show the fact that we illuminate p-n junction with addition of photocurrent generator. So that stands for photocurrent generator in electrical circuit. So it generates photocurrent, which goes partially through the p-n junction as forward current, because under illumination I mentioned that we have forward current and load resistor. So now actually it would be good to come back to this slide. We said that under illumination we have significantly increased drift current by minority charge carriers, and at the same time we have forward bias of illuminated p-n junction. Forward bias means that this potential barrier will decrease. So we had Q times VBI, and it will become under illumination to Q times VBI minus VOC, open circuit voltage. And that will be our forward bias under open circuit conditions. So this barrier drops, so it becomes smaller, and means that diffusion of not much change concentration of majority charge carriers will increase significantly, because we have exponential dependence on the current, diffusion current, and height of the potential barrier. So that means that under open circuit condition, which is steady state, we don't change amount of photons per second which illuminate our solar cell, then we get equilibrium, like steady state concentration of non-equilibrium minority charge carriers, and steady state forward bias because of illumination. So everything is stationary. So under this condition, we will have large diffusion current, and it will be compensated by large drift current, because large diffusion current that comes from the increased significantly concentration of minority charge carriers, and large drift current comes because of forward bias, which we actually build up under illumination and the open circuit condition. So from both sides we create conditions by this photoactivation. When we increase both drift and diffusion current, drift of minority non-equilibrium and diffusion of majority equilibrium charge carriers, and they still compensate each other. So the difference between dark is not fundamental from one side, because in the dark we had also drift and diffusion current compensated each other, and under illumination under open circuit conditions, drift and diffusion current also compensate each other under steady state conditions. However, the key difference that in the dark these currents are small, and under illumination these currents are much larger. And we obviously explain in details why they become larger. So that we need to keep in mind. And now we come back to this equivalent circuit of an ideal p-n junction. So we have this equation. So you remember this equation, we derived this equation, is equation for current voltage characteristic of a p-n junction. So that will define the current which flows through this p-n junction based on the voltage drop over load resistor, which will be equal to electrical current which is generated by this solar cell running like times load resistance. So from this equivalent circuit we can write equation for a current voltage characteristic of a p-n junction under illumination. So that is current voltage characteristic of a p-n junction in the dark, and here we have minus this IL. this is photocurrent, which we generated in solar cell. So why minus? You see that if we open this parenthesis, we will have this positive term. It will be forward branch of the dark current voltage characteristic. And here we have IS, which is I naught we used previously, the saturation reverse current. It will be, for reverse bias, it will be minus IS, because it will IS times minus unity. So that is our negative reverse current. What forms reverse current in PN junction in the dark when we apply reverse bias? Which charge carriers? So we have very small reverse current which flows through PN junction at reverse bias. So when we increase internal electric field and we enhance drift of minority charge carriers. So that is current, drift current of minority charge carriers in equilibrium minority charge carriers, which we have in the dark. So we actually reduce potential, reduce this concentration of equilibrium charge carriers next to the depletion region edges because of extraction. If you recall our lecture about current voltage characteristic of PN junction, you will see that explanation. So the key thing here that reverse current is created by drift of minority charge carriers in the dark, and photocurrent is created exactly the same, in the same manner. It's also created by drift of minority charge carriers, but instead of those equilibrium in the dark with low concentration, by much more minority charge carriers, because we have photogeneration. So it's just much larger than reverse current, but by nature of its formation, it's the same. It goes also in the same direction. That's why when we shine on the solar cell, the current voltage characteristics is kind of shifted downwards. So that's our illuminated current voltage characteristic of a solar cell. And we have here this very small dark reverse current plus this photo-generated charge carrier, photo-generated current, like photocurrent. And they flow in the same direction. They are negative by our definition of what is positive, what is negative. That's why instead of going up, this solar illuminated current voltage characteristic is shifted downwards. So we have actually negative current, large negative reverse current flowing through illuminated solar cell, because that is equilibrium reverse current in the dark, very small, plus very large reverse current, which we call photocurrent now. So it is shifted downwards, and we have such so-called force quadrant of this current voltage characteristic, which we need to consider. So take this away. Now we come to the parameter of like photoelectric parameters of a solar cell. Here we have short circuit current, which comes with sign minus because it's negative current here, because photocurrent is negative and this short circuit current is also considered as negative. So this is for ideal solar cell when we don't have series resistance. It coincides with photocurrent, so we can define this as the following integral. So it's elementary charge times integral from 0 to lambda m, which corresponds to the band gap of the material, like of photon energy at this wavelength, which is already like still larger than the band gap energy. This is total flux of photons at given wavelengths, monochromatic. This is part of this flux which was not reflected because it's 1 time minus reflection coefficient as a function of wavelengths. And this is spectral response or quantum efficiency. So it tells how many photogenerated charge carriers will be created per 1 photon, which actually was hitting the, like absorbed by the semiconductor material. So it's kind of internal quantum efficiency. So we will discuss about this parameter a bit more. Now another parameter is open circuit voltage. So here we have it. Open circuit voltage is defined when this current voltage characteristic overlaps with the voltage axis, means current is equal to 0. So we have like we don't attach anything to this solar cell, and current obviously in external circuit will be equal to 0. So this parameter we can consider when we consider this as 0, and instead we put VOC here. We can from this equation derive expression for VOC quite easily. So that will be kT over Q times natural logarithm of the ratio between photocurrent or short circuit current, because they are the same for ideal solar cell, and this saturation current. So here is +1, but since photocurrent IL is much larger than IS, then we can neglect with this unity and consider simplified equation here. So what do we see here? VOC will increase with light intensity because photocurrent increases linearly with light intensity, and obviously from this equation it will increase. Also, it has in this denominator of the argument in the natural logarithm this saturation photocurrent. So what is important to underline here, that saturation photocurrent is reversely exponentially. So IS is proportional to exponent minus EG divided by KT. So it has very strong dependence of the band gap, and for larger band gap saturation photocurrent will be smaller than for smaller band gap. Means from this equation that for larger band gap IS, which is in denominator, will be smaller, and means that VOC will be larger. So the larger band gap of the material, the larger will be this open circuit voltage. And in the contrary, the narrower band gap we take, VOC will become smaller. So that comes from this current voltage characteristic of the solar cell. And also there is such a parameter as the most useful part, as actually power, what we get out from the solar cell. And power is current times voltage. So voltage drop over load resistor here, and like current I, which flows through this load resistor. So the product of this current and voltage gives us the useful power which we extract from the electrical power which we extract from the solar cell. Now, if instead of I we substitute its expression of JV characteristic, and then multiply this expression for current voltage characteristic by V, so times V, that's what we eventually get. That will be external power, electric power, which is what we can get out from the solar cell. If we look at the voltage dependence of this power, so here will be voltage, here will be power. It will be some curve with maximum. At some voltage V maximum, we will get out from our solar cell maximum power. So we need to, and this maximum power will be equal to I maximum, maximum current, and maximum voltage. So don't mess it up with VOC and short circuit current, because these guys are not maximum current and maximum voltage in external circuit. Because if you want to calculate what power we will get at such short circuit condition from a solar cell. So no, just think in terms of electrical characteristics. Electrical power, what we get out is current times voltage. Current we know at short circuit condition. It's I short circuit. What is voltage? That's by definition 0. So if you multiply short circuit current by 0, you get nothing. So the same stands for open circuit condition. You know voltage, which VOC, but current is 0. So that's why you go from 0 to 0. So it will be VOC, here it goes to 0, and here in this region it will be short circuit current also, but voltage is 0, so it also goes to 0. So maximum current and voltage we need to find from this distribution of power, output power versus voltage, when we have a combination of large current and large voltage. So when the combination of this large, the product gives maximum product, we get maximum current, maximum electric power extracted from the solar cell. So how we find this V maximum and I maximum, as I have shown you, we plot power, external power, which is product of current times voltage, versus voltage. Here we see this maximum point. We can already identify at which bias we have, at which voltage we have this maximum power. Then we put this maximum power here on voltage axis. We extrapolate it towards the point where it intercepts with the current voltage characteristic of illuminated solar cell, and then we automatically find maximum current. Done. So now, when we know all of this, we can introduce the third main photoelectric parameter, which is called fill factor. Fill factor is the ratio between the area, like this dashed area, which is our power, which we can collect in external electric circuit from this solar cell, divided by the area of this rectangular, which is defined by short circuit current and VOC. So ideally, we want to have this dashed area larger, approaching to this VOC times short circuit current, but it's impossible because it will mean that we have collection of all charge carriers which are generated, and there are no recombination and extraction losses. So that's why this fill factor is always smaller than unity. So in theory it can be equal to unity, but that is only for, I mean, that should be always smaller than, should be always smaller than unity.
So this goes like, if we have fill factor where is equal to 1, that means we have a square. Yeah,
current voltage characteristic, which means, I mean, that's ridiculous.
One guy was trying to explain that at Prof. Ashkat's lab when we were measuring the JV characteristics of perovskite source.
Mm-hmm.
And then we after we got the data, he was trying to explain it that we don't want a square.
Yeah,
we can't get a square.
We cannot get it because
I didn't get it that time because I couldn't see it at this point because we are going the fill factor. If we have it that this is square, that means every photo that was
yes,
we have like 100% generation.
We have total extraction of charge carriers of which are generated, which is impossible, and so we can go to up to 90%, but definitely it cannot be unity. And yeah, imagine that we have such JV curve. So we have the same current, short circuit current. We have the same VOC. So 2 parameters out of 3 are the same. So we would say, okay, that's a good device. They have high VOC and high short circuit current. But look here. This area is much smaller because VM much smaller and IM also much smaller. So just this fact that fill factor is much smaller will tell us that this device actually not good, regardless that we have high short circuit current and high VOC. Moreover, let me get rid of it.
So this is also supposed to be like more quadratic enough, like we don't want a linear dependence of the IS.
Exactly. So that is the actually it changes less than unity and it goes more than 0.25 because that is kind of the worst considered case when we have linear, and then in this case it will be 0.25 the fill factor. It will be the lowest factor, fill factor. In some cases can be even worse. Yeah, but that you need to already create some mess up with the contacts. So it could be some like S-shape JV characteristic, which makes it even smaller, but that implies not only bad solar cell itself, but also like bad PN junction and neutral regions, but also bad contacts. So they kind of, instead of extracting, they block charge carriers and keep them inside, so you cannot extract them. So that is really, you intentionally need to make it worse. But the lowest for reasonable, like good ohmic contacts, that's 0.25. And now, when we define all these parameters, we can come with the most publicly interesting parameter, which is efficiency. So we have maximum power, which we can extract from the solar cell, and input power. Input power is integrated this spectral distribution of solar light. So that is 1000 watt per meter square under IM 1.5. And maximum power is defined as product of maximum current and maximum voltage. But from this equation, we can also express this product as I short circuit times VOC times fill factor divided by P input, like input power. So that is efficiency, and we see 3 main photoelectric parameters of the solar cell: short circuit current, open circuit voltage, and fill factor, and all of them are in numerator. So we want simultaneously increase all of them in order to have good device. We cannot keep one low because that will just kill our performance. We need all of these devices to be as high as possible. Now, discussion about band gap. That's important because that is one of the key parameters which defines semiconductor as suitable for solar applications. So here we have some efficiency theoretically predicted, assuming only radiative recombination losses based on detailed balance between absorption of light and radiative recombination emission. So no non-radiative recombination losses, only radiative. That's like fundamentally what we cannot get rid, because if we can absorb, I told you about that before, we discussed radiative recombination quite in details. If we can absorb photon and create electron-hole pairs, that should be possible a reverse process. Should be possible that these guys meet and also generate the same photon because of recombination. So based on this detailed balance and only radiative recombination, theoretically predicted performance, we consider one sun because it could be done for higher concentrations of light, but that is a bit trickier because you need to cool down solar cells, and like we consider normal condition one sun. So you see that the maximum performance is something around 31%. So that is the fundamentally maximum performance of a single junction solar cell. Not tandem. With tandem solar cells you can make some tricks and gain more. But with single junction, that is the maximum possible performance. And that is plotted, this theoretically calculated performance versus band gap of different materials. And we see that we actually get some curve with maximum. So for given spectral distribution, which is shown here, is with black line, we have this distribution of efficiency versus band gap dependence. And we see that somewhere about 1.45 to 1.5 electron volts, that corresponds to the highest possible performance of solar cells. So why we get this? So we will not go into discussion of this detailed balance in details because that requires probably number of lectures itself. But we will, from qualitative point of view, try to understand this. So I told you that input power, which comes to our device, that's integral all over this spectrum. So obviously we want that all photons from at each wavelength generate some charge carriers in our p-n junction, so that we can have a chance to collect them. So from this point of view, we want narrow band gap material because it will absorb here. If we have EG1 and EG2 and EG1 is smaller than EG2, means that we efficiently will use a broader range of solar spectrum. So instead of using only this part for wide band gap semiconductor, because up already here photon energy is not enough to generate electron-hole pair, we could use all this part up to here because we have narrower band gap material. So that will create more charge carriers, non-equilibrium, and photocurrent IL will increase. It will be larger for EG1 material because it will utilize wider spectrum of the solar light. But that's only one side of the story. The other one starts when we recall this equation I showed you for VOC. It's not only, there are three: short circuit current, VOC, and fill factor. So by decreasing band gap, we increase short circuit current, but we also decrease VOC. Moreover, not only decrease VOC, because we have this larger saturation current in the denominator of that equation, but also we need to consider energy losses. So imagine we have as a solar cell, let's say a solar cell photoactive material, germanium. And its band gap is something 0.67 electron volt. So this is EC, this is EV. Now we absorb some photon H nu with energy, let's say 1 electron volt. So that's equal 1 electron volt. So that is energy which came to us. Absorbed by this, oh sorry, it's negative. So this electron will be pushed up to, this will be 1 electron volt, because that's the energy which it got from the photon. But it will not stay here. It will thermalize within 10 to minus 12 seconds to the bottom of the conduction band. So this difference, which will be now about 0.3 electron volts, will be just gone to thermal vibrations of the atoms in crystalline lattice. So we lose this energy, so it was available for us, but we lose it because of thermalization process. So that another factor, besides this equation with lower VOC, which results in energy losses. And that's why we have, from one side, narrower band gap, larger fill factor, larger short circuit current, but from other side, we have smaller VOC and these energy losses. So as a result, we get this curve with maximum, and there is some neat point where we have high enough VOC and low energy losses, but still we absorb quite decent part of the solar spectrum and can maintain quite high short circuit current, and that is in this region of maximum of this curve, which corresponds to band gap about 1.5 electron volts. So the best materials for photovoltaic application, here are some examples for inorganic semiconductors, indium phosphide, gallium arsenide, and cadmium telluride. But at the same time, silicon is not far away, and technology, like silicon is an abundant material, technology is developed quite well for silicon processing silicon semiconductors. It's cheap, it's much cheaper than any of these other solar cells, semiconductor materials, and that's why silicon solar cells are quite spread all over the world for large scale application. Germanium already is much lower, so doesn't make much sense to use germanium for solar cells, but for photodiodes, which we will consider next time, that makes sense because we want to have photosensitivity in a wide spectral range, so we use really very broad range of materials for photodiodes as photodetectors. So here we get, once we already understand how solar cell work, we have three contributions, three type of currents: diffusion, drift, two diffusion currents of minority charge carriers from N and P type region, non-equilibrium photogenerated, and one drift current. So that's our PN junction. Under illumination, some asymmetric PN junction, we have mostly depletion region in P-type side of semiconductor. That's profile for doping concentration distribution, And this is profile for photogeneration. So short wavelengths, they have larger absorption coefficient alpha. That's why they will be absorbed closer to the surface of the solar cell. And longer wavelengths, they have smaller absorption coefficient, so they will penetrate deeper in the material and generate charge carriers deeper. And obviously, because of this non-uniform electric field inside, these charge carriers will be collected and contribute to photocurrent. So let us start with contributions from neutral regions within this diffusion lens. It will be Ln and Lp. So this will be diffusion currents. So we can write continuity equations for electrons in p-type semiconductor and holes in n-type semiconductor. This current, Jn and Jp, we know is diffusion current of minority charge carriers. That's why we don't deal with drift. So that's why current can be considered as diffusion. This is our generation profile, Gp, and this is our recombination. So that is this continuity equation for holes in the n-type region of the semiconductor. Here, from this region, how much because of diffusion we will contribute. So the solution of this differential equation, this continuity equation, will give us Pn as a function of x, distribution profile of minority non-equilibrium charge carriers, which we discussed qualitatively in previously. And by taking first derivative over position, since that will like finding the gradient of this concentration of that profile of minority non-equilibrium charge carriers, we will get electric current, like diffusion current of holes from n-type region of semiconductor of this p-n junction under illumination. So diffusion current of minority non-equilibrium photogenerated holes. The same we can do also for diffusion current of minority electrons in p-type region. So I don't put here explicit equations because they are quite bulky, so you can take a look in Z. This gives like whole solution. We just need to understand how we come to this point. And also we have one more contribution to the current, which is drift current from depletion region. So we assume that internal electric field is very strong, which is true. And all photogenerated charge carriers, these electron-hole pairs, are separated by this strong electric field. That's why we have total flux of electrons which reach the p-n junction, and that part is absorbed amount of this flux in the depletion region. So we just multiply that by Q. So this part actually gives us the amount of photogenerated electron-hole pairs per square meter, like per unit area, within the thickness of depletion region. So total amount of charge carriers per unit time, per unit area in the depletion region. Times Q, it gives us drift current because we assume that all of these photogenerated charge carriers will be collected and contribute to photocurrent because we have strong electric field and they don't recombine. So in total, our photocurrent will consist of these three contributions, which I described you earlier. So it will be diffusion of minority non-equilibrium holes, diffusion of minority non-equilibrium electrons, and drift current, which originates from collection of photogenerated charge carriers in the depletion region. So the last slide for today, we have spectral response, and that is also stands for internal quantum efficiency, because it gives us the ratio between the number of electrons which form photocurrent to number of photons absorbed by the solar cell. So keep here your attention absorbed, because we have the total flux, that's number of photons which hits the solar cell. But here we take into account, we kind of subtract those which were reflected. And that's why we consider here for spectral response or internal quantum efficiency the ratio between total charge carriers which form photocurrent to the total number of photons absorbed by the solar cell. And that, of course, at given wavelengths, because we have spectral distribution of this internal quantum efficiency. So that is, here is like our total photocurrent represented by 3 contributions, divided by Q, that gives us total number of electrons created photocurrent, and that is total number of photons which are absorbed at given wavelengths by solar cell. So that's how spectral response looks like. So here we go from 0 to 1, internal quantum efficiency it also can be called. And we have kind of 3 contributions. First of all, we have contribution of diffusion current from like substrate, it's holes from p-type. Here, like contribution from front region, it's minority holes in n-type, and this is our depletion region contribution drift current. So total spectral response looks like this. And we see that ideal is this dashed line. So it should start at the wavelengths which corresponds to the band gap, when we already take energy of photons which corresponds to the band gap. So at larger energies, it should go to unity and state unity. So that kind of ideal case when we collect all photogenerated charge carriers, but that's not the case, and that's why our internal quantum efficiency of the spectral response is, it depends on wavelengths, as you see, and it is smaller than the unity. So of course we want to have it as high, like as large as possible for all these photon energies. Because then we will efficiently convert this sunlight photons into electricity at each wavelength. And here we can just show how surface recombination is kind of comes from one of boundary conditions for that continuity equation for current voltage, like for current of photocurrent, which we considered. So if we increase surface recombination at the surface of solar cell, like here, for instance, this is surface recombination speed. We discussed this parameter also previously. So we increase it as the larger number, the more recombination rate happens on the surface. We reduce this spectral response quite significantly, so it goes down. So obviously surface of a solar cell should be also carefully passivated in order to prevent all unnecessary problems. And that's why we come back here again to this expression for photocurrent of the solar cell. that's the product of absorbed photons per given wavelength per time per square area times this internal quantum efficiency spectral response, and that is per wavelength. If we want to get total photocurrent, so we need to integrate it from wavelength 0 to wavelength which corresponds to h nu m, which is Eg, because if we go for longer wavelengths, means that h nu will be smaller than Eg band gap, and it will not create photo charge carriers. So so this is defined by solar light. We cannot change this. That's the spectrum of our solar light. This part we can change. We can reduce this reflection by anti-reflection coating, and spectral response quantum efficiency, we need to design solar cell first of all with appropriate material, high quality, with reduced recombination losses, increase extraction of photogenetic charge carriers, and that will help us to increase this parameter. So if we increase spectral response and decrease reflectance, keep this guy constant, we can increase the photocurrent of the solar cell. So with this I would finish our discussion about solar cell. Got a bit longer, but that's important topic which we definitely need to discuss in details. Okay, thank you very much for attention. If you have any questions, you're welcome, and then see you next time.